notes, the topics in the notes. We did, and the homework.
For the solubility rules, is that to be given in a test, or should we memorize it?
You should memorize them. Yeah.
Do you have like a specific way of memorizing it when you're a student, like mnemonic or?
No, but some people do. There's a bunch of mnemonics out for the solubility rules. I just wrote them over and over again. It's not that much. There are only 7 solubility rules, and you can write it very compact. And so I just wrote them repeatedly. I think by the 100th time I had written them down, that they're. If you write them down like 100 times, 500 times, and then right before the test you write them down. And so normally what I would do is if I was ever in danger of forgetting something before the test, I would write it down right before I took the test, and then when I got the test, I would write it down on the test so I wouldn't forget, and then just go from there if it was something difficult to remember. All right, other questions? Yeah, that's fine. You should put the arrow closer to the. If you put the arrow closer to the products. So you could do something like this, If you have it off to the side, I might miss it, that's all. And so I need to be able to see it. How would iron 3 ion and chloroform? Iron 3 ion and chloroform don't mix, yeah. No, because the iron 3 is supposed to react with bromide. That forms bromine, and then you add the chloroform on top of this, and you'll get bromine. Bromide does not dissolve in chloroform, but bromine does dissolve in chloroform. And so if there's a reaction there, you should see a red-orange chloroform there. If there's no reaction there, then the chloroform should be colorless.
Do you want the lab by the end of the day or by the end of the class?
No, by the end of the day is okay. Just if you need to submit it, you can put it under my office door, room Chem 120, or you could just email it to me. It's fine.
Is that why one of my labs came back with a foot? Like a foot print? I'm dead serious. That was like a boot print.
Yeah, sorry. I might
That's
have.
alright. I was just so confused. I was like, did I do that?
Yeah, I must have done that. So.
That's hilarious. That's pretty funny.
I just gotta watch where I step when I walk.
I'm gonna be subjective with the opinion that God is truth. So very cool.
How about anything else?
Can I just turn it now?
You could turn it in up here. All right,
There's 17 through 18.8. Does it look like I'm missing anything?
yeah, just throw it in the pile. It should be. Where did I leave off last time? Because I didn't save the PowerPoint, and then it crashed, and I lost it, the file. It's not working. Try that.
No problem solved. Excellent.
I spoke about heat capacity, correct?
Yeah.
Were we looking at this one with the lead pellets?
No.
So there are three heat capacities that are common. The one that's probably most common that people, let me make sure I'm recording this. Used quite frequently is the specific heat. The only difference between all these heat capacities are the units. Specific heat, you know what the units for specific heat are? This is joules per gram degree Celsius, right? Specific heat of water is one that's not too difficult to memorize. 4.18 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. Did I talk about calories, right? Food calorie and that. The molar heat capacity, all we do is we replace grams with moles. So water is 4.18 joules per gram degree C, but if I have a mole of water, it's 18 grams. So the molar heat capacity is 18 times bigger because we're looking at not 1 gram, but 18 grams. Be a mole. And the third one we have is the heat capacity of an object. You know. And that's when we have objects that aren't conveniently expressed in grams or moles. And this would be like a brick, you know. What's the heat capacity of a brick? And do you want to weigh every single brick you put in a brick wall? No. So if you say a brick is about 2 kilograms or a kilogram or something, then we can figure out what the heat capacity for that object is, and then just multiply. If you have 100 bricks in the wall, you just multiply by 100. And so we did this the other day, except we did for calorimeters. We only ever use 1 calorimeter, so we never change the number here, the amount of calorimeters. The amount of calorimeters is 1. And so the other unit for this would just be in joules per degree C, but in reality it's joules per object per degree C. And so that would be the object heat capacity. And the units for that is in joules per object per degree C. Calorimeters is a special case of that where we only have one object, but if we had bricks, then it would be joules per brick per degree C. So if I have 100 bricks in the wall, then I can figure out.
Man, the syllabus said quantum mechanics. I was not prepared.
Syllabus said quantum mechanics. I'm just far behind. Since I'm far behind, what I'm going to do is I'm going to have the video.
Cool. Is that our fault?
I'm sorry? No. No, not our fault. Yeah, your fault specifically.
Specifically, no one else is involved.
No.
Slow down,
No, it's my fault actually because
guys.
I need to be talking faster. What's that?
Will our exam reflect that?
No, your exam's still going to be chapter 7 right now. I'm going to finish chapter 7 this week, but I'm just going to have a supplemental video. I missed 1 day of lecture, and so I owe you 1 lecture. Although they docked, I pay, but it's all right. We'll have 1 extra day. We'll see how it goes. So when an object warms up or cools down, it's absorbing or emitting energy, or there's going to be a transfer of heat, that is kinetic energy. And whenever we have a transfer of energy, we pay attention to the law of conservation of energy, or the first law of thermodynamics. The first law of thermodynamics says this. if a system loses or gains, the surroundings must gain or lose, so that the total heat never changes. The amount of heat in the universe is fixed. And so we have the sign convention for this. Did I talk about the sign convention for heat? So if Q of the system is less than 0, it's negative, then Q of the surroundings must be positive. And so when Q of the system is negative, it means it's lost energy. Where did that energy go? That energy went into the surroundings. So if the system is minus 10 joules, the surroundings must be plus 10 joules. That way, the total energy of the universe stays constant, fixed. If the system gains energy, then we say the Q is going to be greater than 0. And that's a gain that's here. That means the surroundings must have lost energy. So the surroundings must have a Q of the surroundings less than 0. So now let's take a look at a calorimetry experiment here. If you look at this calorimetry experiment, take a look at this calorimeter. This calorimeter is quite fancy. In fact, this calorimeter is so fancy, what they're going to say is that it's so well insulated that it really doesn't absorb any heat. In fact, they're going to say it absorbs so little heat, we're going to call the heat capacity of the calorimeter 0. If the heat capacity of the calorimeter is 0, then there's no heat absorbed or lost by the calorimeter. So I could have a hot calorimeter, it's not going to give any heat to cold objects. Or I could have a cold calorimeter and it's not going to absorb any heat in the cold object. And so you'll see in your book, in the homework problems, you'll see some of the homework problems will just make an assumption. The calorimeter is ignored, basically. So what that means is if I have some hot lead here, I'm going to dump this hot lead into the water, and it's only the water that absorbs the heat. Normally, if I dump hot lead into the water would absorb heat and the calorimeter would absorb heat. Both would absorb heat. But in your homework, most of the problems up to the integrated advanced are going to assume the calorimeter doesn't absorb any heat. And that goes even for the thermometer. The thermometer is going to absorb heat. If the thermometer doesn't absorb heat, then there's no way the temperature can rise. You know? And so by its very nature, a thermometer must be able to absorb some heat. The other thing is, in this case, what we're going to do is we're going to dump the hot lead into the water. But I didn't put the hot object into the cold. What I did was I put the cold object into the hot. Do you know why? That's what we did when we did the calorimetry experiment yesterday. We poured the cold water into the hot versus the hot water into the cold. Why would it make a difference? Yeah, it's going to cool down too much. And so as soon as you remove the lead from the boiling water bath, what's going to happen to the temperature? It's going to drop. And then when you pour the lead beads into here and it comes into contact with the cold air, the temperature is going to drop again. And so by the time that lead hits the water, it's no longer at 100 degrees C, it's well below. But since this is a homework type problem, we don't care about that. We're going to assume that the lead is going to maintain a temperature of 100 degrees C until it's mixed with the cold water. And so in this case, that error is not going to be present. And so what we're going to do is we're going to label our lead the system. It doesn't matter what you label the system or surroundings. And then we're going to figure out the system is going to lose energy. So we're at 100 degrees C of kinetic energy. We're going to put it in here. The water itself is at 22 degrees here. And so if we bring the lead into the water is going to absorb heat. And you'd expect the calorimeter to absorb heat, but this calorimeter has zero heat capacity, so we're going to say the calorimeter doesn't absorb, including the thermometer. And so the only thing that absorbs the heat will be the water. All right, so the hot lead will cool down, and the cold water will warm up, and then they'll reach an equilibrium temperature. And this temperature is going to be the same for both. So the final temperature of the lead and the final temperature of the water will be at 28.8.
Do we get to pretend like this isn't a calculus problem?
Yes.
Okay, awesome.
Yeah. Calculus is not required for this class at all.
Excellent.
However, somebody was asking about pressure,
Vapor pressure or just oil pressure?
gas pressure. So I was talking about that. We'll probably mention that here. And pressure can be treated as a calculus problem if you want.
With respect to what?
Respect to density
Density? Oh, I see.
and composition. The density of air and the composition of air changes as you go up in altitude continuously. And so their calculus would be very useful.
I didn't say I did.
So in this particular problem, we have Q of the system is going to equal minus Q of the surroundings. And what we're going to do here is this. Q of the system is the lead cooling. And if the lead cools, then we need to know the amount of lead, the grams of lead, times the specific heat of lead, times delta T of lead. And this is equal to minus Q of the surroundings. So the surroundings we're going to make very simple. The surroundings should be Q of the water plus Q of the calorimeter. But we're going to say the calorimeter absorbs no heat. Therefore, that's going to be 0. We're going to assume it's so well insulated that no heat is lost. And so this problem is going to simplify into just Q of the water. So Q of the water is going to be minus the mass of water times the specific heat of water times the delta T of water. And then we're going to solve for the specific heat of lead. And so this is called experimental determination of specific heat. And so since we know the specific heat of water, we know it takes 4.18 joules to warm up a gram of water by degree C, we can just measure the temperature change of 50 grams of water, and then we can determine how much heat is absorbed by the water. Well, all that heat came from the lead. And so if we know how many grams of lead, and we know the delta T of lead, then we can determine the specific heat of the lead. Here. So since I lost this, so let's take a look at this here. Well, maybe I'll just do it this way. So let's go ahead and complete this calculation. So the mass of lead is going to be 150 grams. Times the specific heat of lead, which is our unknown, times delta T of lead. Delta T for the lead is going to be T final minus T initial. So T final is the final equilibrium temperature here, which is 28.8 degrees C, minus T initial, which we're assuming is 100 degrees C because it's boiling water. So I'll assume that this is 100.0 degrees C here. And then we're assuming all the heat that's lost by the lead goes into the 50 grams of water and not the calorimeter. So we're going to have 50.0 grams of water times the specific heat of water is 4.18 joules per gram degree C, times delta T for the water. Delta T, it's the same T final, 28.8, but the T initials is only 22.0. This will be in degrees C. So let's solve for this. Specific heat of lead. So I'm going to get my calculator out. And so I'll just do the delta T first for water. 28.8, this is our T final, minus T initial is 22. That's 6.8 times 4.18 joules per gram degree C times 50. And that gives me 1421.2. This is minus. Joules. So the water absorbed that, although the sign's wrong. The sign's wrong because I have this equation here. And then I'm going to take this and divide it by 150. That's how many joules was lost by the lead. .0 grams of lead times my delta T. The delta T here is going to be 71.2 negative. So I'll do my 1421 divided by 150 divided by 71.2. And I get a specific heat of lead of positive 0.133. Let's see, I'm allowed 3 sig figs, 0 joules per gram degree C. And so I know this is a specific heat because of the units. It's joules per gram degree C. All right, so this would be the experimental determination of the specific heat of lead. This specific heat of lead, how does it compare to other specific heats? And so let's take a look at that. I'm going to delete this page. And so if I look at a table of specific heats, we could determine these experimentally just like we did over there. We would probably not assume that the calorimeter is perfect. We'd probably just assume it's just a regular calorimeter. And determine the heat capacity of the calorimeter first, by mixing water like we did, and then use that heat capacity in this calculation. But going back to this, it's 0.130. 0.130, you look at it, and it looks like it's on the lower side or the higher side of specific heats. It's on the lower side. If you look at the specific heats in this table, they vary from 0.130 to 14.3. And so it's low. So it has a small specific heat. If it has a small specific heat, what does that mean? What it means is that it heats up rapidly. Something, it doesn't require much energy to increase the temperature quickly. So if you had a burner and you heat some lead, it's going to get hot fast. What's on the high side? Well, 14.3 is really high, right? But when you look at the bulk of them are way below 14.3. So if we ignore 14.3, what's the highest? Water, 4.18. And so what we say is water has a high specific heat. Water has, and I mentioned this before, but in biochemistry, the first chapter is always water. You know, some of the properties of water that make life feasible. And one of the properties is the high specific heat of water. You know, it's what we call a good heat sink. Sometimes when you're working with hot metals, you'll have a bucket of water, and you can cool the metal down rapidly. You just throw it in the bucket of water, quenches the heat. And the same goes for anything. You can quench it. You got to be careful with other things because you could have what you call failure, and in other words, it's fractures due to mechanical failure of the structure. And we call that thermal shock. And so we don't want to thermal shock things, but water's great at quenching heat and cooling things down. If you need to cool things down, spray water on it, cools it down. And so water has a high specific heat. Metals tend to have low, like copper. Iron has a bit higher. So if you built a frying pan out of lead, it would heat up rapidly. You wouldn't want to build a frying pan out of lead because some of the lead will get in your food. But we could use copper. Copper is a bit better, but not as good as lead. Gold is very low too. If gold was on this table, it'd have the lowest specific heat. So if you could build a frying pan out of gold, man, that would heat up very fast.
It would also melt.
What is the melting point of gold?
It has to be near a butane flame, right? It's not that high.
Yeah.
You can boil tin over the stove.
Yeah. It would be pretty cool. Gold has a surprisingly high melting point.
Really?
Yeah, surprisingly high, but I don't know the number. Platinum, I had gold and platinum cookware in the chemistry lab. Why gold and platinum? Because gold and platinum they're very unreactive. And for some of the chemicals I was using, they would react. Like if I was using ceramic cook pot, or if I was using iron or copper or lead, they would have been eaten away. And so I used a lot of platinum. Platinum has a melting point of 1600 degrees C, which is extremely hard. In fact, I was using platinum cookware in a platinum oven. This platinum oven had a platinum coil, so the platinum oven could reach temperatures of 1600, degrees C, which is over 2000. What's that?
What were you doing?
Doing lots of different things. Trying to fuse or get elements to react. Yeah. So one of the things I was trying to make a superconductor ceramic, superconducting ceramic, and it required extremely high temperatures. So you mix the things in there, some barium, some other elements, copper. The copper melted, and so when I was using the ceramic, the copper would melt and start reacting with the ceramic. I was using aluminum oxide from ceramic, then switched to platinum. But some people. That was when, so it was just sitting in the lab and in an open drawer like this. It was worth a lot of money then, but now, the prices of that kind of stuff is skyrocketed. And so I just can't imagine how much money is in that drawer right now. It's huge. we have a little piece of platinum wire. It's a tiny piece of platinum wire. And I think if you lose that, it's like a $200 lab charge, you know. Yeah. I may be exaggerating that. I got to take a look at the price list again. But it's ridiculously expensive. Hydrogen is very unusual. Do you see that? 14.3. That's extremely unusual. In fact, you know, like Fukushima and Chernobyl, they suffered meltdowns. You know, the temperature got too hot. But this new series of nuclear reactors that they're looking at using hydrogen, you know, because of its high heat capacity.
Fusion reactors or normal fission reactors?
I'm sorry?
You mean fusion or fission reactors?
Fission reactors. Fission reactors will suffer meltdown. I remember Fukushima. And then I remember the U.S. government. I think Clinton was offering to supply the Japanese government with some kind of secret cooling agent. You know, I was thinking secret cooling agent.
Wait, no, 2011. I'm sorry, that would have been Obama.
Secretary of State
Oh.
Clinton. And then they said, no thanks, we don't need it. And I'm thinking, no thanks, why not get some of the secret cooling? I mean, even if there's a remote chance of meltdown, you know, later on people found out why they refused the offer. They refused the offer because it had already melted down. And so, but this is stuff, you know. Actually, my friend of mine is a nuclear engineer on a nuclear-powered submarine, and I was thinking, you know, what happens if something's getting too hot? It's going to melt down. Usually they have water. They just pump water through the reactor. Apparently the diesel water pumps, well, they had electric water pumps. Those failed, and then the diesel ones got flooded, and those failed. And you think, okay, they only have one backup, you know, generator. If you have something like that, like some nuclear reactor, you'd think they'd have multiple backups, right? Like, okay, if the diesel generators fail, then what? Because, you know, engines, you know, my engine, you know, like, did I mention I blew up my engine, the Subaru? And I'm thinking, you know, what if that happens to your diesel generator and your nuclear power plant and it's about to melt down, and, you know, and then sometimes it doesn't start? You know, how long has it been sitting? Do they start it every day? You know, if it's been sitting for a while, sometimes you like cross your fingers. Is it going to start today? Hopefully. But you would think there'd be more backups. But then they're talking about this the secret nuclear subcooling fluid, and I'm thinking, oh, that sounds very interesting. You know, because I was reading about this other thing in space. They have these boxes that have some stuff to as a heat sink, and then I was reading some more about it, and it's this guy. Just puts wax inside these boxes, and they take them out to space to act as heat sinks, and the wax melts. And I thought, wow, you know, in a way it's so simple. In another way, I don't know how much he charges for those, but it's probably an awful lot of money. And you're thinking it's just some piece of wax in a box, you know. But anyway, so they're looking at hydrogen now in the latest generation of nuclear reactors. You know, and they're looking at very compact nuclear reactors, and they're proposing these for like data centers or whatever for AI. You know, I guess it takes a huge amount of power to run AI. So anyway, so the thing is, you want to look for patterns here. So we're looking for patterns. Metals are very low, and other things like more complex not metals, but these are not metals. These more complex molecules have higher heat capacity. So one of the things you might hypothesize is that metals, all they can do is vibrate. But something like water, what can water do? Water can vibrate, it can rotate, and it can translate. And so you think, well, there's more ways that water can absorb energy. You know, metals don't have very many ways they can absorb energy. And so that might be a hypothesis, but then why is hydrogen so high? Because hydrogen is such a simple molecule. All you have are translations and vibrations, only one vibration. Water has 3 different vibrations and rotations. And so why should hydrogen have such a high specific heat? And so these are things, the questions that come up when you look at the data here. We're not going to get into it. Later on, we'll talk a little bit about specific heats of these, or heat capacities of these. So in the next section, we're looking at heats of reaction in calorimetry. So we just did a calorimetry experiment. The calorimetry experiment was to measure the heat of an object. The object was a bunch of lead pellets. And so when we have an object, objects cool down or warm up, you know, when you put them into contact with hotter or colder objects. And so in calorimetry, we can measure heats. There are two types of heats we measure. The heats associated with the object or heats associated with reactions and processes. So if we have a reaction, let's say we have a combustion reaction, it releases a lot of energy. And where does all that energy go? It goes into the surroundings. And it goes into the surroundings as heat. The surroundings are going to warm up in a combustion reaction. And so in calorimetry, we have two types of calorimetry we do. Actually, two types of systems that we study. And the two types of systems that we study are the objects and reactions and processes. So I wrote down here, 7.2, we're looking at objects, you know, hot object and cold objects in calorimetry. In 7.3, we're looking at reactions. So when we're looking at reactions, what happens in the reaction is that there is a change in chemical potential energy. Because when we deal with reactions and processes, we don't want to change the temperature. If we change the temperature, then we have to deal with multiple equations, and it becomes a hassle. And so here, we just want to look at changes in chemical potential energy only, or just potential energy. And so the chemical potential energy is associated with the bonds. So the bond's strong. If the bonds are strong, it's not very reactive. You know, like the nitrogen in this room. The nitrogen in this room has a nitrogen-nitrogen triple bond. The nitrogen-nitrogen triple bond is extremely strong. It takes 1,000 kilojoules of energy to break just 1 mole. 1,000 kilojoules per mole. And so some people say that nitrogen is a pseudo-inert gas or pseudo-noble gas because the noble gases are very unreactive, because it takes a lot of energy to take electrons from noble gases.
How many kilojoules?
1,000 kilojoules per mole.
So when you see a lightning strike and you see that brief flash of plasma, do you think
That's
how are they gonna
more.
react your bonds? It's more?
That's
That's
more.
only per mole.
That's more.
Boring.
Ionization energies are higher. When you see a lightning strike, you're breaking bonds, and you're creating ions in the lightning strike. Yeah. So we have heat of the reaction. So heat of the reaction, what we do is we make sure we do these at constant temperature. Constant temperature just means the final temperature and the initial temperature are the same. And so before reaction, it might be a room temperature, and then at the end of the reaction, it should go back to room temperature. It doesn't mean the temperature stays constant all the way through. And so if you burn something, let's say we're looking at the heat of combustion reaction. The heat of combustion reaction, you burn something, it's going to get very hot. And so the temperature increases, but we wait until it drops back down to room temperature. It cools back down, and then that's what we call constant temperature. And so this is what I'm saying here, is if we have an object, we take an object at high kinetic energy, that is a hot object, and this hot object loses heat to another object, and then it becomes a cold object. The other object is surroundings. Whereas in Q of reaction, we're looking at potential energy. So the potential energy might be high, like methane and oxygen, and then we let it react to CO2 and water. And in that process, we go to a lower potential energy, and this is going to release kinetic energy to the surroundings. And so we're going to lose heat as kinetic energy to the surroundings. But we're really losing potential energy here, because it's not a hot object transferring kinetic energy to a cold object. I have, maybe this is a little bit confusing, but we'll see it again. I'm going to write it a different way. So when we have a reaction, we don't have hot reactants. You know, the hot reactants cool down. In the process, they transfer heat to the surroundings. Now, we have reactants that are room temperature, and this would be like a combustion reaction. And during the combustion process, everything gets hot. You know, combustion methane gets close to 1,000 degrees C. But what we do is we wait for it to cool down, and eventually it's going to cool back down, so the CO2 and water that are generated are back down to room temperature. And now what we've done is we've released the maximum amount of energy to the surroundings. If we start off with reactants here, and we have the products at a higher temperature, let's say the products we stop here, that means we haven't released all the energy from combustion into the surroundings. There's still more energy that needs to be dissipated into the surroundings. And so to accurately measure the total amount of heat, we gotta wait. We gotta wait until it completely cools down, and then we know how much total energy was released.
Room temperature?
Yeah, well, whatever temperature you start off with, you know, what's the most common temperature? Would you say 0 degrees C or room temperature? Room temperature. So if somebody doesn't mention the temperature, you automatically assume they must be talking about room temperature. You wouldn't automatically assume they're talking about 0 degrees C, you know, STP. Although somebody assumed it. On the last test, I didn't specify the temperature, and so they weren't getting the correct answer on the multiple choice. And it was because they had assumed 0 degrees C, whereas I had assumed room temperature.
I wonder the average temperature of the dark side of the moon. Could it change this?
That's a homework problem from chapter
Is it actually?
1. Yeah. Well, it just says, you know, or maybe it was the temperature swing.
Because they've got
Yeah.
no atmosphere, so the sun heats more, but also...
It does have an atmosphere. Yeah.
What?
I don't know what it is, actually. Does somebody know?
A gas?
Well, maybe if it the situation is if it had 0 atmosphere, do you know what the pressure would be? 0. That would be a perfect vacuum, but it isn't. You know, it's not a perfect vacuum on the moon. There's stuff on there. Perfect vacuum's hard to achieve. Nobody's achieved a perfect vacuum on Earth. So when I was working with materials, these scientists, I went to a talk and they were talking about this experiment that they were going to do on the space shuttle. So what they wanted to do is they wanted to grow single crystal semiconductors on the space shuttle, but not inside the space shuttle, outside the space shuttle. They thought if they grew it outside the space shuttle, then that would be even better than a clean room. You know, clean room is there's things they can't completely get rid of all the dust and whatnot in a clean room. And so they did it. They grew single crystal semiconductor, like chips type thing, out in space. They brought them back to Earth. They analyzed them, and they were much, much dirtier than anything they could grow on Earth on clean room. It was from the pollution from the space shuttle. The space shuttle was degassing all kinds of stuff from the tiles. You know, they have these.
I feel like rocket scientists would consider that.
Yeah. Yeah, you would think so, because on Earth, you know, when you do stuff, you have to degas. It takes so long. So usually what you do is you bake it in the oven and you subject it to a pretty high vacuum and degas the surface. Otherwise, there's a whole bunch of stuff that's trapped on the surface. And the surface of those, they have these aerogel tiles. Have you ever seen those things? Yeah, those are crazy, extremely light and just really almost like a perfect insulator, heat insulator, thermal. So if you built like the calorimeter out of aerogel, cups rather than styrofoam, then your heat capacity of the calorimeter should be close to zero, It just depends on how tightly you can seal the lid, and then you got the head space there where there's air trapped there. The same goes for endothermic reactions. Endothermic reactions get cold and then you gotta wait. Because if it gets cold and you stop there, then it still needs to absorb more energy to get back up to room temperature. So this is what they call constant temperature. They call constant temperature only the initial and the final temperature are the same. And pretty soon we're gonna start thinking in terms of only initial and final. Have you heard of state functions before? In thermodynamics, we deal a lot with state functions. A state function doesn't care how you get there. All it cares about is the final and the initial. Right? So a state function might be a temperature change. Let's say we went from 0 to 100 degrees C. So what's delta T? Delta T is 100 degrees C. We went from 0 to 100. But it doesn't care how you got there. You could have started at 0, went to 12,000, and then dropped back down to 100. Delta T is still the same. It's still 100 degrees C, even though you went to 12,000. And so we'll be looking at state functions more. And so this is why it's kind of weird. You think it's constant temperature. No, it's not constant temperature. It's just the final and the initial are the same. So here's a reaction or process. This would be the surroundings here. And you see the surroundings have, well, they've warmed up. The surroundings used to be at room temperature. And they mix this together. Now it's hot. Now what do they have to do? They have to wait until it cools all the way back down to determine the total amount of energy. If you look at this is at 5.8 degrees C. So this is very cold. And so this is an endothermic, that's an exothermic. So we're not monitoring the progress necessarily. We just want to know at the beginning and at the end what has happened. So this is what this keep in mind thing is about. Keep in mind that the temperature of a reaction mixture usually changes during a reaction. So the mixture must be returned to the initial temperature before we assess how much heat or energy is exchanged. So whenever we deal with a reaction or process, if the initial temperature and the final temperature are the same, then there's no change in kinetic energy. The only change is in terms of potential energy. We don't have to do this. We do this to make the math easier. You could, if you want to, stop there. But it makes the math more difficult, and the final interpretation of the results is not. So straightforward. So the next thing here I'm going to talk about is this. We have other types of calorimeters. This one is called a constant volume calorimeter. And this is called constant volume calorimetry. Normally when we think in thermodynamics, we either are in the constant volume world or in the constant pressure world. If we're in constant volume world, then we think in terms of which law? Dalton's or Avogadro's? Constant volume. When we're in the constant volume world, we think in terms of Dalton's law. And Dalton's law just says what? Dalton's law says that the pressures are additive. Right? The pressures can change. So this is why this is called a bomb calorimeter. It's called a bomb calorimeter because the pressures can become extreme. Extremely small or extremely big. And therefore, we need a steel bomb to withstand the pressure changes due to Dalton's law. Yeah. So let's take water as an example. If you have a mole of liquid water, how much does a mole of liquid water weigh? 18 grams. And how many milliliters is 18 grams of liquid water? 18 milliliters. So 18 milliliters is not that big. Okay, then I'm going to vaporize all that water. If I vaporize all that water and have 1 mole of water vapor, water gas, 1 mole of gas occupies what volume? So 1 mole of gas occupies a volume of approximately
I forgot the exact number. It's
24.5 liters. That's a number that's useful to remember. I wouldn't bother remembering 22.4 or 22.7 because those are the molar volume of a gas at STP. And so you're going from 18 milliliters to 25 liters. That's a pretty huge expansion in volume. So you're going from this volume to this volume. Can your bomb withstand that pressure increase? Well, let's hope so. Otherwise, what's going to happen is going to explode due to a pressure explosion. Or let's say you're going from 1 mole of gas, 25 liters, to 18 milliliters. So you just collapse the volume. When you collapse the volume, you create low pressure. When you create low pressure, that's called a vacuum. Because you still have 14.7 pounds pushing out here, but if you collapse this so that the pressure is extremely small, what can happen? Implosion. And so the bomb here is to prevent implosions and explosions from happening because we've got to worry about Dalton's law. The pressures are additive. And so when we do constant volume calorimetry, we do it in this bomb. And therefore it's called a bomb calorimeter, and the technique is called constant volume calorimetry. Why would we want to do something in a bomb like this? Why we want to do something in a bomb is, like say you want to combust some sugar. If you combust some sugar, can you do that in styrofoam cups? No, it's not going to work. And so we're not going to do styrofoam cup calorimetry. We're going to do bomb calorimetry. So we'll put some sugar in here, burn it. All that energy from combustion is going to go into warming up the surroundings. And so what are the surroundings here? The surroundings are, we have the steel bomb, we have these wires, we have this plate here, we have the air in here, and then this bomb is underwater. So we have all this water, and then we got this stirrer here, and the thermometer, and then we have this case here. And so everything's going to absorb heat or energy from combusting the sugar, including outside here, the rest of the universe, because this is probably not perfectly insulated, and so some heat will leak out. The stir makes sure that there are no hot spots and cold spots. Because this is why, because were you stirring, after you mix the hot water and cold water, did you stir it? You didn't stir it? If you stirred it,
15 seconds.
we stir it because, like say your bath is too hot, so you get a bucket of cold water, you dump it in there. Do you have to stir it or does it mix instantly? You have to stir it, otherwise it doesn't mix, and so you'll have hot spots and cold spots. So, and that's because of the diffusion rate. Diffusion's kind of slow because there's so many collisions. There's so many collisions in the gas phase, huge number per second. In the liquid phase, there's even more collisions. So let's say you try to walk in a crowded room. The room is totally packed with people. How long does it take you to walk from one end to the other? Well, it depends on, how much you can push, your way through, but it's going to take a long time, longer than a gas. And so diffusion's slow. And so this is why the stirrer is there. The stirrer is to make it more homogeneous. So usually we have a stirrer there. And that's because we don't have 1,000 thermometers. If you had 1,000 thermometers, then you can just average the temperature maybe. But we just have one thermometer over here, and it's hot over here, and it takes too long for the heat to travel over there, and then we might have missed it already. So when we measure this, of course, we want to measure it in the middle at the peak temperature, and then let things cool down. Okay, so you have the stirrer. So what we need to do then, we need to weigh how much iron is in the bomb. And then we have to weigh how many grams of ceramic is here, and then the grams of wire, and then the grams of water, the grams of glass in the thermometer, and the grams of metal in the stirrer, and then the grams of metal in this enclosure, and the grams of air outside. Do we do that to get the specific heats of everything? No, you know what we're gonna do? Is we don't even care how much water is in here. What we're gonna do is we're gonna put a standard, like a primary standard. A primary standard in this case is something that we know how much. Let's say 1 gram of this standard releases 1,000 joules. And so what we got to do is we got to put a standard in there. And what are standards used for? What process? They're used for calibration. And so what we have to do is we have to calibrate it. And so we put something in there and burn it. And then we know how much heat's released because that's a standard. The standards are well known. And so if it releases 1,000 joules into this, then we look at the temperature. And then we get the heat capacity of the calorimeter. The heat capacity of the calorimeter is just going to be taking the joules of heat and dividing it by the delta T. And so C of this calorimeter is just equal to the joules of heat divided by delta T. And so we need something that has a known amount of heat. And so what we're going to do is we're going to treat the calorimeter, this is Q, the calorimeter, as being everything. The bomb inside here, the water, the reservoir surrounding it, the wires, plus everything else. And then we're not going to look at one by one. The whole thing's going to absorb heat. And then we'll calibrate. So the first step in using this is calibration of the bomb calorimeter. Once we have it calibrated, then we can put an unknown in here, burn it, see what the temperature rise is, and then calculate how much heat was given from that. So a bomb calorimeter is good for like combustion reactions. And so this is why it says wire for ignition. It's to ignite it. But what it measures is something called Q sub V. Bomb calorimetry measures Q sub V. And the V means constant volume. Then we have the coffee cup calorimeter. The coffee cup calorimeter, there are fancier versions of this, better insulated cups. And there are things that are extremely small calorimeters that they have you can use. But so we have the coffee cup calorimeter does not measure Q sub V, it measures Q sub P. P stands for constant pressure. So if we're in the constant pressure, which we are, right now we're in constant pressure, then which law applies? Dalton's? No, because Dalton's law, the pressure changes. We're in Avogadro's. In Avogadro's, what changes? Not the pressure, the volume changes. They're saying a simple calorimeter, well insulated, therefore isolated. I don't believe it's isolated.
That's magical thinking.
Yeah. Q the reaction is equal to minus Q the calorimeter.
What if we put this calorimeter inside another calorimeter so we know precisely how unisolated it was?
You
Now
could
we're
do
thinking
that.
Now we're thinking.
Yeah, that's possible. That would work. I wouldn't bother memorizing this equation because usually we do Q, the reaction is equal to something inside the calorimeter plus the calorimeter.
Wait, but the second calorimeter is equally unisolated, so its calorimeter is all the way down. Infinite regress.
Yeah, but what we do is you really don't have to do that because all we do is, yeah, if it's leaking out heat here, that's just going into the rest of the universe. And so you just have a leaky calorimeter, but it's already kind of compensated for. You could do it to find out how leaky the calorimeter is, so that would be good. The first calorimeter. So in our labs, we didn't do it like this, you know. Most of our ones was Q, the reaction, is equal to Q of what's left over after the reaction plus Q, the calorimeter. You gotta see what kind of junk is left over after the reaction. It could be water, it could be salt solution, it could be sodium hydroxide. And so whatever is left over after the reaction is going to absorb the heat from the reaction. The heat from the reaction, this is kind of weird because the reactions it's not like a hot object. You know, when we're saying heat from the reaction or heat of reaction, it's the change in potential energy. That change in potential energy is making heat. Another way of thinking about this is like if you have a battery powered heater. If you have a battery powered heater, are the batteries hot? And these hot batteries are transferring heat to your, you know, I was looking, they have like battery powered socks, heaters for socks. Have you seen those? So like some skiers like these things, they have these battery powered socks. So are they just taking hot batteries and putting them in your sock and then transferring heat that way? No. And so what it's doing is it's taking chemical potential energy and then the energy is transferred as heat. It's making heat because the objects, your socks, are going to absorb that energy. And when objects absorb energy, they get hot. All right, it's important that we identify whether we have a QP or QV, because you could do the exact same reaction in a constant volume world or a constant pressure world and get different amounts of energy. And so sometimes QP and QV are not the same for the exact same reaction or procedure. And so we need to know, are we measuring QP or QV? One of the things with QP is that we have to be careful that we don't make a bomb. Like, for example, here, if you did your KClO3, and I know this happened to somebody, right? Where you stopper it, you stopper it too tightly, what's going to happen? Well, when you decompose the KClO3, it's going to generate oxygen. And let's say you didn't let's say you accidentally pinched the hose or something. And then as that oxygen is being generated, if the volume can't expand, the pressure is growing. And if the pressure grows too high, you know, either the test tube is going to explode or the stopper is going to shoot out. Fortunately, it's just the stopper that shoots out and the test tube doesn't explode. But it happens that also depends on how fast that happens. So when we do things at constant pressure, we got to allow volume to change. So if we're generating, let's say, a mole of oxygen gas, the volume's got to increase by 25 liters, or let's say less than a mole of oxygen gas. Let's say I don't have a full mole of KClO3 or something. It makes 3/2 O2. Well, let's say in this case, let's say the volume had to expand 1 liter, like this. And volume expansions and contractions must occur when we're generating gas or consuming gas. That's the primary. there could be small changes in volume because KClO3, does KClO3 have the same volume as KCl? Not exactly, because they don't have the exact same density. And so there's a very small change in volume here, but that's a very small change is kind of negligible compared to the huge change here. You know, it's not going to be like a 25-liter change going from KClO3 to KCl. And so your book is often going to ignore the volume changes for solids, and they're going to ignore the volume changes for liquids. But when we have gas, like let's say there's no gas here, and all of a sudden we have gas now, there's going to be a significant volume change. Now when we have a volume change, that's work. And the type of work that we deal with here is called pressure volume work. Pressure volume work is required to maintain constant pressure for reactions or processes that generate or consume gases. That's what I wrote here. So we need to do some work here in order to maintain that constant pressure. And so one way of thinking about this is like this. Let's say you want to blow up a 1-liter balloon. If you blow up a 1-liter balloon, does it cost any work? Or is it free? Let's say not just one balloon. Let's say you had to blow up 1,000 balloons, all of them 1 liter in volume. Is that going to be a lot of work? It's going to be a lot of work. How much work is that going to be? Well, we want to know how much work that's going to be. And so this is, again, called pressure volume work. Well, how much work that's going to be depends on how much volume you need, and it's going to depend on the pressure you're fighting against here. And so we have 14.7 pounds pushing down on this. Here, so you're fighting that. And so this came up, this is why I was talking about pressure earlier. You know, and there are a couple of things that I still wanted to mention about chapter 6. One is pressure. You know, in the ideal gas law, can you use Celsius? You have to use Kelvin, right? And the difference is Kelvin's absolute temperature. We must use absolute temperature in the ideal gas law because 0 Kelvin means something. Whereas 0 Celsius, does 0 Celsius really mean anything physically, chemically? Not really. I mean, just freezing water, but it doesn't mean anything to hydrogen. You know, does something special happen to hydrogen or helium at 0 degrees C? Absolutely nothing. You know, helium would be totally blind to 0 degrees C. Nothing would happen to it. Okay, just like temperature, we have to use absolute pressure in our gas equations. We cannot use relative pressure. Relative pressure is called gauge pressure. And so if you go to a tire gauge on a car or a bicycle and it's reading 0 psi, is that really?
That's really bad news for you.
It's bad news, but does that mean there's no gas inside? There's no air inside your tire? You know, if it were absolute, you know, an absolute pressure of 0 psi means there's nothing. It's totally empty. And so this is what people want. They want to grow these crystals at 0 absolute pressure. Would be kind of nice because then there's nothing in there. No gases to contaminate your crystals. It'd be hard. And people are trying this because it's cleaner and cleaner. But there's still air inside your tire. Even if your tire gauge is reading 0, in order to get the air out of there, you'd have to suck it out. And you probably wouldn't be able to suck it out because your lungs aren't strong enough to get absolute 0 pressure. If they are, then, you know, contact these semiconductor crystal grower people. They just spent a lot of money on trying to grow crystals in space. But we need to do that. And so it depends on where you blow up the balloon. If you blow it up and there's 0 pressure out here, then it doesn't cost you any work. You know, it depends on how much pressure. And so this is absolute pressure here. And so, so the reason I was saying about this is, if you try to blow up a balloon 10 feet underwater versus blowing a balloon above the water, which would be easier, to blow the balloon on the pool side or to blow up the balloon underwater? Above water. Because if you're 10 feet underwater, that's about 1.3 atmospheres, versus poolside, you might be at 1 atmosphere pressure. Versus, let's say, Big Bear. If you drive up to Big Bear, that's like 5,000, 6,000, 7,000 feet of elevation. You know, like if you bring if I drive up to Big Bear, I bring a bag of chips or something. You see it's trying to blow itself up. You know, I didn't even have to work. It's like blowing up its own balloon. That was easy. But there it would be easier to blow up because the atmospheric pressure is lower. And so there was one thing I wanted to talk about, and this is, since you mentioned calculus, you might use some calculus for this. Oh, I got logged out. I wasn't sure if I signed this as homework because there are a lot of end of chapter problems missing out of Mastering Chem. But we have noted that atmospheric pressure depends on altitude. And so as you go higher in altitude, what happens? The density of air decreases. Whereas for liquids, the density stays fairly constant. So we need calculus for that because as we go up in altitude, the density is getting lower and lower and lower. And so things that are continuously changing are best handled by calculus. The other thing that changes is the composition of the air. Down here, air is about 80% nitrogen, 20% oxygen. But as you go up higher and higher in elevation, do you know what happens? It becomes more enriched in the lighter elements or compounds and less enriched in the heavier ones. The heavier ones tend to settle at the bottom. And so we get less and less oxygen. Oxygen's lighter than nitrogen, or no, oxygen's heavier. Oxygen's heavier than nitrogen. So oxygen is more enriched down at lower altitudes, and we'll have more nitrogen at higher altitudes. And so the composition's changing. So if both things are changing, then calculus is a nice way to handle that because, you know, the pressure is going to depend on those things. And so we have this atmospheric pressure as a function of altitude can be calculated with an equation known as the barometric formula. Was this a homework problem? The barometric formula? Remember liquid pressures are just given by mgh. Over here, this air pressure is given by P is equal to P naught times 10 to the minus m. M is the molar mass of the gas. G is the gravitational constant. H is the height, altitude, over 2.303 RT. And so in this equation, P and P naught can be in any pressure units. For example, torr. P naught is the pressure at sea level. It would be 760 torr, or 1 atmosphere. Generally taken to be 1.00 atmospheres or its equivalent. The units in the exponential term must be SI units, however. Use the barometric formula to A. Estimate the barometric pressure at the top of Mount Everest in the Himalayas. Altitude 23,035 feet. So I did this calculation before, and it's about 1/3 of an atmosphere at the top of the Everest. I usually only assign part A. Part B I don't. But mountaineers are familiar with this. Show that the barometric pressure decreases by 2/30ths in value for every 1,800 feet increase in altitude. So mountaineers want to know, how the air pressure is going to drop with altitude. That way they'll know if they need oxygen or not, or at what point they'll need oxygen, Or they might go oxygen free, might not bring a tank of oxygen.
Well, I really doubt them are completely oxygen free.
Well, I mean, not bring up a tank. I mean, that's pretty impressive to climb that. I mean, I went up to the top of Mount Whitney and that just killed me. That's only 14,000 feet.
Yeah, I went to Denver with that inhaler and I was dying. I'm not built for that.
Yeah. Well, anyway, we can figure out how much work is done here. The amount of work, we can relate it to mechanical work here. And so this is mechanical work. Mechanical work is the force pushing an object over a distance. And the force is going to be related to the mass of the object times g, the gravitational constant. And the distance, in this case, we're going up and down, so it's delta h, or the height that we need to lift this. And so what we do is, okay, this is not moving, but we're going to let this gas expand by removing one of these masses. If you remove one of the masses, then the gas expands. How much does it expand? It expands this much. And this much expansion is going to require this much work. It's the mass times g times delta h. And so that's how much work was done. So we can calculate the amount of work using an apparatus like this, but an apparatus like this is kind of a hassle, with a vacuum. And so instead, in thermodynamics, they do this a lot. In thermodynamics, they look for thermodynamic relationships. Thermodynamics is a bit of a pain because there's so many different equations in thermodynamics. It seems like there's 1,000 different equations there. And you derive them by doing different relationships like this. And so what they did here was they multiplied and divided by A, the area. So the force over unit area is just the pressure. And the height times the area is the volume. And we're looking at the change in height, and so that would be the change in volume. So we come up with this equation. This equation says that the work is equal to minus P external delta V. And so rather than this vacuum pulling this up, what we're going to do is we're going to have a pressure here, and the gas has to fight that pressure here. And so what we'll do is we'll do a little calculation here. The calculation here is we're going to say that delta V is 1 liter. So V initial is 0 liters, V final is 1 liter. So delta V is V final minus V initial. So we have a volume change of 1 liter. And then P external is P atmospheric. We're going to say P atmospheric is 1 atmosphere, just normal atmospheric pressure. So how much work did we do? So we plug that into this equation here. Pressure volume work. Pressure volume work is minus P delta V, P external delta V. P external is 1 atmosphere, so this is minus 1 atmosphere, and then we have delta V, 1 liter minus 0. And we get the work. How much work was done? How much work was done is 1 atmosphere liter of work. 1 atmosphere liter of work, or 1 liter atmosphere of work, is energy. Energy. How much energy is that? And so this is a very odd unit, an atmosphere liter or liter atmosphere. It's an odd unit, but it's related by here. So if we want to know how liter atmospheres and joules are related, then we take the R value. We take the R value, 8.3145 in joules per mole Kelvin, and divide that by the R value in liters atmosphere per mole Kelvin. And so do you see liters atmosphere is the same thing as energy? It's energy per mole Kelvin. That's the R value. And so we do this division, 8.3145 divided by 0.08206. Cancel out the units, moles cancel, kelvins cancel, and we're left with joules per liter atmosphere. And what it comes out to is it comes out to 101.32 joules per liter atmosphere, or 101.3 joules per liter atmosphere. So if you blow up a 1 liter balloon against a P external of 1 atmosphere, then how much work did you do? You did 100 joules of work. So if you blow up 100 balloons, that's 100 times that.
That is in contention for the worst unit, the worst compound unit I've ever seen. What's the worst one you've encountered?
They're worse than this. Yeah. Maybe Planck's and some other stuff. Planck's because it's hard to visualize. This is a little bit easier to visualize because the liter atmosphere is just blowing up a balloon, 1 liter balloon against the pressure of 1 atmosphere.
It's about that much, right? About that much is a Planck, right?
I don't know. A Planck is very small. A joule times a second is a weird one. A joule, Planck's, we'll talk about Planck's constant in the next chapter, but it's a unit of action.
That's even worse, right? Like horsepower watts.
Yeah,
A joule
sort
second.
of. It's kind of, it's still weird to
Wait,
think
is it
about.
full second watt?
Hmm?
Never mind, I'm assuming.
But we'll get to that. We'll see some other ones that are kind of weird. And so this was 1 liter atmosphere, therefore it's 100 joules. That's 100 joules of work that just did there. All right, why are we interested in such stuff? And so we're interested in this. We got to keep track of these things, you know. QP, QV, constant pressure calorimetry, constant volume calorimetry, work. You know, we want to keep track of all that stuff. Okay, then we're going to come back to the first law of thermodynamics. So this is kind of a repeat. The first law of thermodynamics can be expressed in many ways. Q of the system is equal to minus Q of the surroundings. And that's primarily for heat, you know, heat. But we also have work, and so we got to factor in work. And how do we factor in the work? And so we're going to look at the first law of thermodynamics, where we look at a change in the total energy. Delta U of the system is the change in internal energy, the total energy of the system. So when we get to the first law, we're interested in 2 major things: delta U of the system, and one other thing called delta H of the system. Delta H of the system is the change in enthalpy of a system. And so what we want to do is we want to know what's the difference between delta U and delta H, and what are they used for. What they're used for is to make calculations. Like, say, I want that primary standard I'm going to calibrate my calorimeter with, my bomb calorimeter with. That primary standard, I need to know either delta H or delta U for that. And if I know delta U or delta H, then I know how much heat is going to be evolved per mole. If I know how much heat is going to be evolved per mole, then I can figure out how much heat is going to be evolved per gram. And so delta U and delta H are going to be very useful numbers to know so that we don't have to do calorimetry all the time. If you know delta U and delta H for a reaction, there's no need to do calorimetry. You already know the results of your calorimetry experiment, what they should be. And so these are going to turn out to be the most useful things, because there we can predict how much energy. I don't have to measure it. I can just predict how much energy I'm going to get. Not just for calorimetry, but for everything. And so we're going to first look at delta U. Delta U is called the internal energy, or the total energy. U is the total energy, not delta U, sorry. Delta U is the change in total energy. U is what we call the absolute internal energy versus delta U. Delta U is a change, U is the absolute. And this is the total energy. Total energy is the sum of the potential energy and the kinetic energy in a system. Potential energy we call PE. Kinetic energy we call E sub K. Now, as far as kinetic energy goes, let's look at water. Water is a good heat sink because there are a lot of ways water can absorb energy, whether it's potential energy or kinetic energy. Water can absorb this energy, and when it absorbs it, then it can increase its kinetic energy here. And so water can translate, it can rotate, and it can vibrate. This is showing the 3 kinds of vibrations of water. Do you know water can vibrate like this? you could vibrate like this, where this bond compresses, this bond expands. So it's really weird. It's like a dance, a lopsided dance or something like that. And then water can vibrate like this, where the oxygens stretch out like that. And so there are 3 ways. These are called vibrational modes. Yeah, basically. If it's an ideal gas, the only thing we have is translational energy. And you know the equation for translational energy. Translational energy is 1/2 mu squared. Can calculate 1/2 mu squared. That's for translational. Rotational kinetic energy we can calculate, but you don't have the equation for rotational kinetic energy. Rotational kinetic energy is beyond the scope of this class. So we just deal with ideal gases or monatomic gases. But we can calculate also the equation you can find. The vibrational kinetic energies, we can calculate those. You just find the equation for these. And so we have the kinetic energy for that. So if we want to know the total energy of the water, then we have to know its kinetic energy. And we can calculate the translational without too much difficulty, rotational with a little bit more, and vibrational with a little bit more difficulty. But if I want to know the total energy of water, then not only do I have to know its kinetic energy, but I also have to know its potential energy. So how do I determine the potential energy of water? To determine the potential energy of water, I have to look at these types of things here. So this is for the potential energy here. So write PE. So the potential energy is going to be in the intermolecular attraction. So we have hydrogen bonding interactions mainly. And do you know how much energy it takes to break these hydrogen bonds? Not much. It takes about 25 kilojoules to break a mole of these hydrogen bonds. 25 kilojoules is not that much.
Do I make 25 kilojoules in a day?
Yeah, I hope so. I don't know, 25 kilojoules. How many calories would that be? Let's say about 4, 6.
It's calculated.
Yeah. It'd be like 6 calories. 6 food calories. Yeah.
Definitely make that.
Yeah, I think you probably eat more than 6 calories a day. Yeah.
It's so rude.
Then we have bonds. How much energy does it take to break a bond? Like a hydrogen oxygen bond is like 430, 450 kilojoules per mole. It takes a bit more energy. That's to break the first one. After we break the first one, to break the next one costs more, even more energy, like 500 kilojoules per mole. Then we have potential energy. The reason I'm thinking about this is because energy is conserved. So if I break the hydrogen bond, that costs me 25 kilojoules per mole. But if I form the hydrogen bond, you know what that does? It releases 25 kilojoules per mole. If I break the hydrogen-oxygen bond, that costs me 450 kilojoules. But if I form that, it releases that much. And so this is what we call stored energy or potential energy. There's potential energy in there. And then the electrons. In redox reactions, we don't just break the bonds. We also knock electrons off atoms, give them to other atoms. And so we got the electrons. And then if you're a nuclear chemist, then you got the nucleus. You got to break certain pieces off the nucleus. And so there's a lot of potential energy stored in there, etc. So I wrote etc. here. So are these calculations easy? Maybe not too bad for these first 3. But when we get to the nucleus, we got to break apart the nucleus, protons and neutrons. Then we got to break apart the protons. Protons are broken up into even smaller pieces called quarks. And then can you break up the quarks into even smaller pieces? You know? Or quarks, can you? You think so? And then, you know, those mini quarks, can you break up the mini quarks into micro quarks? You know? And so when does it stop? And when it stops, you're at absolute zero. So do you know where absolute zero for potential energy is?
0 Kelvin.
We know where absolute zero for kinetic energy is. That's 0 Kelvin. But not for potential energy. So I'm going to stop here, but you know, I'm going to put a video catch-up lecture. So take a look for that. I'll try to post it soon.